Now we have to deal with electric potential caused by multiple point charges. Since potential, like energy, is a what? It's a scalar. We can just add the magnitude of the potentials. This is why electric potential is so much easier than electric fields, because we do not have to worry about directions. All we got to do is add the magnitude of the potentials due to this Q charge causing the potentials, and when you combine them, you just simply arithmetically, you don't have to use vectors, just arithmetically add the sum of the KQ over R's. So for example, for 3 charges that are causing a potential at some spot, it's KQ1 over R1. Here's Q1, here's R1 to that point, plus KQ2 over R2, here's Q2, and here's the R2 to that point. And if there are other charges, you'd add more terms. So let's take a look at this example right here. For the picture below right here, I'm going to set V equals 0 and R equals infinity, and we want to find the V, the potential at point 3, at the start. Notice that unlike fields, I do not need any angles. It's awesome. It's so much easier. What's the potential at this point? If Q1 is R13 away from point 3, Q2 is R23 away from point 3, what is the potential at point 3? V at 3 is KQ1 over R13 plus KQ2 over R23. You just add them arithmetically. No angles needed. It is about 1,000,000 times easier than dealing with fields. If you want to figure out the field at this point, it would take a long time. It took us 20 seconds to get the potential at that point. This is why we would prefer to use potentials. So now let's figure out the next step of this is what is the work required to assemble these 3 charges? What's the work required to bring these 3 charges together? And when we say that, we mean where are they going to start? You got to assume they start infinitely far apart, and we're going to bring them all in together. And if you understand the conceptual way to do this, you'll be able to reconstruct this from scratch. So all we got to do is bring in these charges one at a time. And we're going to just use E initial plus work non-conservative equals E final for every single step of the process. Let's start with this. How hard is it to bring in charge 1? So nothing's here yet. We're just going to bring in charge 1 from infinity. In other words, we're bringing charge 1 in from into an empty space. What's the field in the empty space? Field is 0. How much work is required to bring in charge 1? You might guess, bring in Q1 from infinity, the work done is 0. We don't need to do any work. It's free. There's no force on charge 1. We just bring this out from infinity right to there, and it's there. Took us no work at all. There's no field there yet. But now let's bring in charge 2. How much work would it take us, we're the work non-conservative, how much work would it take us to bring in Q2 to this point? Well, let's use conservation of energy again. We start off with bringing in bringing Q2 from infinity. We start off with U initial plus work non-conservative equals U final, but our U initial is 0 at R equals infinity. So the work non-conservative, if you just solve for doing this, it will simply be equal to the difference between U final minus U initial, but U initial 0, so it's just U final. It'll be Q2 times the electric potential caused by Q1. So this, right here, what we're looking at, this is the work to bring in Q2 from infinity once Q1 is already there and causing a field. So now our last step, which is the hardest, how hard is it to bring in Q3? Now keep in mind that now both of these charges are there, and they both contribute to the potential at that point. So to bring in Q3, it's the most work of all. And again, using bring in Q3, U initial plus work non-conservative equals U final. The work just to bring in Q3, and this is only Q3, is Q3 times the potential or voltage caused by the other two. It's Q3 times KQ1 over R13. Here's R13. So the potential at this point due to RQ1 rather is KQ1 over R13. And then to that potential, we add the potential caused by Q2. Here's Q2, R23 away, and here's the potential caused by Q2. So here's the potential caused by Q1, potential caused by Q2, and then you multiply Q3 by the total potential caused by those two charges. So this right here, this whole thing, that's the work just to bring in Q3. So what's the total amount of work to assemble those charges? We just add all that up together. All that work is just Q1, Q2 over R12 plus Q1, Q3 over R13 plus Q2, Q3 over R23. That is the total amount of work to assemble these three charges if they started at infinity.